So I've started the recording, so may as well get underway. So last time, I've unfortunately fallen into that pattern of I don't finish topic last time, the class before, and so I had to do a reintroduction to it, but hopefully we'll get back in line today. Whatever we're going to say about symplectic toric manifolds, we'll say it today, and then we'll be done. So last time I had introduced this idea of a symplectic toric manifold. So it's a compact symplectic manifold with a faithful Hamiltonian action of the torus. And the dimension is twice the dimension of the torus, which is the biggest it could possibly be. The dimension of the torus, the biggest it could possibly be. So the dimension of the manifold is as small as it can be if you fix the dimension of the torus. So it's got kind of the most Hamiltonian torus action you could have. And we talked about this kind of remarkable theorem that tells us that symplectic toric manifolds are completely controlled by their moment map image. So you take the moment map image, you get a subset of the dual of the Lie algebra. Since I'm really writing Tn here, I'm thinking of not just a torus in the abstract, but actually the nth Cartesian power of the circle. That dual of the Lie algebra is canonically isomorphic to Rn. And so I have a subset of Rn. The kind of subset of Rn it is it's always a polytope. And it always has this special integrality property of being Delson, which is basically a property about the slopes of the edges as they meet at each vertex. So sort of, as I said before, I kind of prefer to think of it as at each vertex, you have n hyperplanes coming in and facets if you use the polytope. Those all have integral normal vectors, and those normal vectors are a basis of z to the n. And we'll see today what the significance of that property is. Well, that's sort of arises very naturally from the geometry. All right, and of course that moment map, the moment map isn't canonical. I can just add any scale, not any scalar, but any constant element of T dual to it I want. So that polytope is really only well-defined up to translation. But if I get the same polytope up to translation out of two different symplectic toric manifolds, they're actually T equivariantly symplectomorphic. All right. So what do I need to prove? Well, I need to explain why the moment map image of a symplectic toric manifold is a Delson polytope. I need to explain how you can take a Delson polytope and construct a symplectic toric manifold whose moment map image is that polytope. And I have to explain why that's unique. And kind of all of these things, I'm going to do a little bit of a sketch. I don't think I'm going to try to get every single detail of any one of them. But I think all of these are kind of, they're not easy to prove, but they're easier to prove than you might guess just looking at this statement. That this seems crazy. Like, how would you get a handle on what a symplectic toric manifold is? How would you see that the moment map image is a polytope? How do you check something like that? All right, so I'm gonna address these points in this order. So first I'm gonna talk about why is it if you have a symplectic toric manifold, the image is a Delson polytope. And the kind of key starting point, I have to admit, I'm going to do things, somehow what I'm going to say, it must be equivalent to what's in Canis de Silva, but the ordering is very different. I don't know, somehow like it's kind of hard for me to follow exactly what's going on in a lot of that discussion in Canis de Silva. So you're getting kind of my take on it, but it must ultimately be pretty much equivalent. So assume we have a symplectic manifold. And now I'm not making an assumption about the relationship between the dimension of the manifold and the dimension of the torus. In fact, at least initially, I'm not even assuming that the group is a torus. So start with symplectic manifold. Its dimension is 2D. Yeah, I'm not even going to assume it's compact yet. And assume that I have a compact group. Sorry, and I should have said acting Hamiltonianly. On M. So assume that I have a compact group and it acts on M in a Hamiltonian and particular smooth way. And I should even say there's nothing really special about being Hamiltonian here. We'll see the significance of that in a moment. If I have a fixed point for the action of this group, then there's a version of the Darbuth theorems. The Darbuth theorem tells us, just thinking symplectically, that point has a neighborhood which looks like R to the 2n as a symplectic manifold. And in fact, rather than say R to the 2n, it's more natural to say the tangent space to M at that point, which is of course a vector space of the right dimension. That's a symplectic vector space. And our manifold looks locally like the tangent space as a symplectic manifold. And the theorem is for compact group, that's true G equivariantly as well. So there's actually a neighborhood. It must be a G invariant neighborhood of the point such that it's G equivariantly symplectomorphic to an open subset of the tangent space at P. So near a fixed point, equivariantly for compact group, your manifold looks like the tangent space. And this is nothing, there's nothing really truly symplectic going on here. I mean, there's a little bit because I have to make sure that I get Darboux coordinates. But this theorem is also true non-symplectically, that if you have a compact group acting on the manifold, here the group representation on the tangent space. But there's something special and interesting we get out of this because we're doing it in the symplectic case, which is, well, we restrict the moment map to that little neighborhood, and then it's going to have to, up to addition of a scalar, or again, addition of a constant, I should say, it's going to have to be the linear moment map that we discovered. So up to translation in T star, there's a specific form that moment map takes. And we'll only talk about this for Taurus because that's a bit simpler, but the same principle applies for any group. The other reason it's sort of particularly nice to think about this as a Taurus is Taurus actions have a lot of fixed points, whereas actions of other groups might not. Actions of non-abelian groups quite often just don't have any fixed points. All right. So what this is telling us, it gives us a local form for the moment map of the group, which I'm now going to assume is the torus T to the n acting on the tangent space. And the easiest way to do this is to say that as a real vector space, but as a symplectic manifold, this tangent space is isomorphic to Cn. And the T action on the tangent space is by multiplication by unit complex numbers on each of the coordinates. Now there's a way to say this that only involves real numbers, but then I have to write out the 2 by 2 matrix for multiplication by e to the I of this guy. And it's much just easier to write it in a complex way. This is maybe a little bit of a hint that I'm always sort of secretly thinking about algebraic geometry, like it's not coincidence that you can make this a complex linear map, but you could just regard this as I'm doing everything over the real numbers, and this is just kind of a convenient way to write the formulas. And what does this action look like? So I'm just, something you always have to be kind of careful about in this picture. I'm always going to be thinking of T to the n as Rn mod 2 pi z to the n. So I'm like not exponentiating. So in order to turn this into a complex linear map, then I have to apply an exponential. So what I'm doing here, what does this action look like? Well, I have some vector, which has to have integer entries for everything to be well-defined. And I'm taking the dot product of an element of the torus, thought of as this quotient, with that integer vector. That gives me a result that's a well-defined element of, well, let me just write, if I have an element of the torus thought of this way, I can write its dot product with some uk. So this is in Tn, this is in z to the n. What I get is a well-defined element of r mod 2 pi z. So it makes sense to look at ei raised to that power. So e to the I t dot uk, that's a perfectly good unit complex number. Okay, and so what's happening here, this is a statement about the representation theory of a torus, is my tangent space breaks up into two-dimensional subspaces, which I can identify by C, and the torus acts on that by rotation, by mapping down to a one-dimensional subtorus, which this UK tells me which one-dimensional torus I'm mapping down to which S1, and then that S1 just acts by rotation on the complex numbers. And any so any representation of the torus is going to look like this. My moment of hesitation there is you have to worry about the trivial representation, which is one-dimensional. But when you put a trivial representation, has to come with another trivial representation coming with it to make the symplectic form work out. That corresponds to when UK is 0. So thus far, we haven't said anything that would exclude the case where UK is 0. That's fine. All right. So are there any questions about this statement? This is kind of a fact about the representation theory of S1 effectively. Okay, so then what does the moment map for this action look like? Well, we already know what the moment map looks like for S1. So now we just have to think about carefully what happens if I project down to some quotient group, have a Hamiltonian action of that guy, and then pull back that action. And if you sort of parse everything through, what's happening here is the moment map, oops, sorry, this is on, I messed up my indices here. This is on C to the D. And similarly, this is C to the D. I haven't assumed that my torus has half the dimension of my manifold yet. All right, so what the moment map is going to look like is I have my complex coordinates, and we remember that the moment map for rotating one S1, C by an S1 is minus 1/2 the norm squared. So now we get minus 1/2 norm squared times UN. And this is in Rn, which I identify with the dual of my Lie algebra. All right. So, and this is of course only up to addition of a constant. Addition of a constant. So my moment map, if I have a global moment map and I restrict it to a little neighborhood around the fixed point, it's going to be of this form up to addition of some constant element in R. All right, so this tells us something rather interesting about the moment map image. The moment map image is going to be, of that little neighborhood, is going to be a rational cone, kind of the tip. I'm going to have my U1, U2, U3, etc., right? And my moment map image, well, there's that annoying minus sign. So actually I should take minus all of those guys. And my moment map image is going to be the cone that I get by taking the ray spanned by these guys and taking the sum of all points in those rays. All right, so this is kind of your first hint that polytopes should be appearing. That near a fixed point, I get something that looks like a corner of a polytope, the region around a vertex in a polytope. Cool. Now, since D is totally arbitrary, I could get anything here. I could get the whole neighborhood around the origin. I could get a big complicated cone with lots of different rays in it. But for the symplectic toric case, it's much more restrictive. So if D is equal to N and the torus action is faithful, then actually that tells you that UM must be a basis of Z to the N. So if it didn't span Z to the N, then there would be some element of the torus that was acting trivially on the whole neighborhood around that fixed point. And one of the details I didn't fully sort out for myself is why does that mean it acts trivially on the whole manifold? But I think you can get that. So you have to have something that spans Z to the N as an abelian group. So it has to generate Z to the N as an abelian group in order for the action to be faithful. And because D is equal, then it must actually be a basis of Z to the N. It must, and those vectors, those are exactly the edges coming out of this vertex, right? So I'm using these U's in the way Canis de Silva does as the integer vectors that point along the edges coming out of the vertex. And so the fact that these must be a basis of Z to the N exactly tells me that this corner satisfies the Delson condition. So as I said, sort of out of the geometry, just out of this fact that the dimensions match and my action is faithful, the Delson condition pops out immediately. All right. And there's one reason I wanted to do this first is there's another kind of interesting condition about this. So there are a lot of pieces of this proof that are kind of pointing at little hints of much more interesting stories. And one of these is, what does this tell us about, oh, I should have said this. Assume that N is equal to 1. So I'm considering the case now of a circle action. So I'm getting a function to R given by my moment map. And you can check if the fixed point is isolated, that means that all the UKs are not 0. So a fixed point is isolated. It doesn't have any other fixed points in its neighborhood if and only if UK is not equal to 0 for all K. Note for the N equals 1 case, these UK, these are just integers. And so the function locally around that point looks like, let me just write this out, mu is equal to, and I'm just writing the same formula from before, UK minus 1/2 log z squared. All right, so this is a Morse function, right? This is like essentially the definition of a Morse function, that locally around your critical point, your function looks like this. So it's a non-degenerate critical point, and the Morse index of that non-degenerate critical point is the number of these UKs that are positive times 2. So it's going to be important later that all of these Morse indices are even. So if you're sort of used to Morse theory, this is telling you something really interesting about the topology of the manifold, that you don't have any odd Morse index critical points. So for example, you can't have any odd cohomology or homology. And this is a really sort of powerful idea in symplectic geometry, that if you have a moment map, you should try to do Morse theory with respect to the moment map. Right, and so in particular, critical points of the moment map are exactly the same thing as fixed points for your S1. So a moment map for an S1 action with isolated fixed points will be a Morse function. And actually the moment map is a Morse function if and only if all the fixed points are isolated. All right. Okay, so that's sort of interesting stuff about what happens near a fixed point, but that, and we sort of saw a hint of the polytope coming out, but how do we sort of see the whole geometry of the manifold? Well, there's actually a general theorem we can use that if we have any connected compact symplectic manifold, and now any dimension, I'm not assuming it's symplectic toric, its dimension is 2D, it has an n-dimensional Hamiltonian torus acting on it, but there's no relationship between D and N. Always true that the moment map image is a polytope. It won't necessarily be a Delson, but it will be a polytope. And in fact, it will be the convex whole of the image of the fixed points. So again, this is one of these facts that just sounds like, how do you check something like that? It sounds so crazy. And I'm not going to do a formal proof, but kind of, again, it's one of these things that, at least from my perspective, I think it's easier than it looks. I don't know, it's one of these facts you look at it, you're just like, how would you ever prove something like that? And it's sort of not so bad to see the kernel of the idea. So the proof is by induction on n. And so it's useful to note when n is equal to 1, I'm getting a subset of R, and it's the image of a connected manifold that's compact. So it must be an interval, right? For n equals 1, this is just, I have my manifold, it maps down onto R, and because the manifold is connected and compact, it has to hit a connected and compact subset of R, and that's a polytope. All right. For n greater than 1, at least the way I like to think about this is think about what happens when you do symplectic reduction with respect to an S1 inside your torus. So there are a bunch of these coming from every line with sort of rational slope, any line that points in the direction of something in z to the n. And we can consider reduction with respect to that S1. So we take the pre-image of some moment map level for that single S1, which means we take a hyperplane inside T dual. And well, we get a reduced space, and that reduced space still has an action of the torus mod this S1. And the moment map image for the reduced space is my original moment map image intersected with a hyperplane. So somehow the key kind of fact you should keep in mind is a set is convex if and only if its intersection with every hyperplane is convex, right? in dimension 2, that's just the statement that its intersection with every line is connected. And then when I go up in higher dimensions, well, if I have some line that's bad, then there's a hyperplane containing that line, and I can intersect with it and see the problem. And you can rightly complain that this story isn't going to tell you about every hyperplane, because it only tells you about ones whose normal vectors are rational, but it's an issue that can be finessed. All right, so it would be lovely to just say, by induction, the moment map image of this reduced space is a convex polytope. And I just said it's enough to check the intersection with every hyperplane is convex. But there's something you have to watch out for there, which is, so it's automatic that X red is a symplectic manifold, but it's not automatically a connected symplectic manifold. So proving that requires using a fact from Morse theory, which is that if I have a Morse function, so let's assume for now I have isolated fixed points. Again, one of the issues I'm just kind of leaving out, we can finesse, I'm trying to get the big picture here. So my S1 that I chose, it has some moment map attached to it. And if we're lucky, that will be a Morse function. And if I have a Morse function on a connected manifold with no index 1 critical points, so in particular, if it has no odd index critical points, it has no index 1 critical points, then all of its levels are connected. So it's certainly possible to have a Morse function on a connected manifold whose levels are not connected, but you have to have an index 1 critical point in there, right? You need something like, so I'm not going to do an excellent job of drawing this. Let me draw the level sets of a function, and I think we'll get the idea. So if I have a function whose level sets look like this, right? This is the kind of thing you'd have to worry about, where I can have a Morse function that looks like this. I have a level set here, which is disconnected. I can't even really see that. Okay. So I have a level set here, which is disconnected, but the whole space is connected. But exactly what happens here is the level where the two things join is exactly an index 1 critical point. So what's happening here, this is an index 1 critical point. And if you know Morse theory, this is an easy fact to check, right? You can construct your manifold by gluing on handles, one for each critical point of the Morse function. And the only kind of handle where the boundary isn't connected is a degree 1 handle, right? Right, if I have any higher dimensional handle, its boundary is connected, so it can't glue together two different components. All right, so that's the basic idea. I'm going to leave out lots of details, but that's the idea of how you prove that this guy is convex. And basically what you have to do in general is use kind of Morse theory, where you allow your critical point to have some degeneracies, but degeneracies that aren't too bad, and So it's not awful, but it requires a bit of work. All right, so it's convex, that's good, but there are lots of convex things which are not polytopes. So this hasn't proved yet that it was a polytope. What will prove that it's a polytope is if I show it's the convex whole of the fixed points. There are finitely many fixed points. By the way, convex whole just means the smallest convex set containing those points, and the convex whole of finitely many points is always a polytope. So why is this true, that it's the convex whole of the fixed points? Again, I don't think I'm going to prove this in detail, but the basic idea, well, for n equals 1, this is an easy fact, right? The image of a compact manifold under a map to R is the convex hull of the image of the critical points. I mean, this is sort of a dumb statement, but it's a convex set, and the extremal points are critical points of the function, right? Because it's compact, it achieves a maximum and a minimum, and we know that those are going to be critical points of the function. So if the function is the moment map for an S1 action, those are going to be fixed points. And there might be ones showing up somewhere in the middle, but definitely the outer edges are going to be fixed points. And I'll just note here, what does convex hull mean in R? Well, I take the smallest convex set containing these points. So I take the 2 farthest away points, and I take the interval joining. That's all convex hull means in R. So in the higher dimensional case, let me not sort of get too deep into this. But the thing you can check is that if X is not a fixed point, then it lies on, if I have a point in the moment map image, which is not the image of a fixed point, then it lies on a line between points with bigger stabilizers. And again, the kind of thing you should think about doing is, oh, well, if it's not a fixed point, then there's some S1 that doesn't fix it. I can look at the moment map level for that S1. I can apply the theorem down there, and oh, that means that my point lies on some line in that hyperplane, which hits 2 extremal points of the polytope associated to the reduction. And those extremal points have bigger dimensional stabilizers. And then if you're on a line between points with bigger stabilizers, well, if those aren't fixed points, then they're on lines between points with bigger stabilizers. And eventually you find a way of writing yourself as a convex linear combination of the images of fixed points. So yeah, don't worry too much about this sort of in depth. The other way I find useful to think about this is, if you're not a fixed point, then the derivative of the moment map is not 0. So it must be that there's some direction through your point where you can vary your position upstairs along some path upstairs, and then map that down and get a path. So let me draw this properly. I can have some path upstairs whose tangent vector isn't killed by the derivative of the moment map. And then when I go downstairs, well, that means I get a path going through here, again, which has non-zero derivative, which means I can't be sort of an extremal point of the polytope or of the convex set, whatever it is. I have to sort of go through here this way, go through here this way. So, you might think about things like, why couldn't you have a sphere as the image of a Hamiltonian torus action on a compact manifold? And it's because if you take any point on the boundary of the sphere, this argument tells you that the derivative of the moment map must be 0 there. Because you sort of can't have enough directions where this is okay. And so you must have infinitely many fixed points. And that's no good. No good. So you can sort of only have finitely many points that don't contain some little bit of a line. And those must be the vertices of your polytope, or you must be a polytope, and those must be the vertices. All right, so that's my slightly holy argument for why the image has to be a polytope. And our calculation before showed you that near each fixed point, so near each vertex of that polytope, you have to satisfy the Delson condition. And being Delson is just a condition about what happens at every vertex. So you also see why you don't get any integrality conditions on like the distances between points, because that doesn't show up here. It's just something about what's happening near the fixed point. So it's sort of something about slopes, but not something necessarily about distances. All right, any questions? Okay. So now I have to go the other direction. I have to ask, okay, if I start with a Delson polytope, how do I construct the corresponding symplectic toric manifold? And I think the most natural way to do this, and this is what Canis da Silva does, is to use symplectic reduction. So as I was mentioning at the very end of class last time, we construct an affine map from Rn to Rd for D bigger. Doesn't have anything to do with how we were using D before. It's just some number. Well, it's not just some number, actually. D is going to be the number of hyperplanes. I need to bounding my Delson polytope, which I'm going to call delta. So in particular, I had this half space definition of delta. Delta is all of the elements of Rn such that the inner product of X with some VI's is less than or equal to lambda I. And so D is the number of these inequalities I need. And every one of these inequalities gives me a hyperplane bounding delta. And of course, this could always be redundant, and it's actually going to be okay if there are some redundancies here. It ultimately won't change my construction, but you could also imagine just saying no, like, you know, if you take a sort of minimal set of these inequalities such that if you forget one of them, you get a bigger set. So using that definition, the sort of natural thing to do is to send Rn to Rd by sending X to, well, this inner product with each VI minus lambda I. So the first entry is the inner product of X with V1 minus lambda 1, etc. So I'm going to do a silly but useful example. What happens when delta is just an interval in R? So this is kind of the easiest imaginable case, but it will hopefully illustrate what the heck is going on. So in that case, I have two bounding hyperplanes. So my D is going to be 2. And my inequalities written in the form I want are X is less than B and minus X is less than minus A. And let me just, for the sake of completeness here, so this means that V1 is the vector 1, V2 is the vector minus 1, and lambda 1 is B, lambda 2 is minus A. So now my map, well, I have the inner product with the vector 1, that's just X minus lambda 1, so X minus B. and the inner product with the vector -1, so minus x, minus minus a, so plus a. So if I think about what happens when I map into R2 this way, well, I get the affine subspace of R2 defined by the sum of my two coordinates is a minus b. And because of that stupid minus sign in the moment map for the action on C, I want to have a negative number here. And if I look at what happens, okay, so I'm mapping R in via that affine map, and this exactly sends the interval from A to B to this blue interval I drew here. It's the intersection of that affine subspace with the negative quadrant in R2. And okay, this is a special example, but the same thing happens everywhere, that I can always map in Rn to Rd affinely this way. And I've exactly set this up, right? So that you lie in delta if and only if all of these entries are negative, right? So I could rewrite this inequality as the inner product of x with vi minus lambda I is less than or equal to 0. So I'm writing my delta as taking the negative orthant in Rn, or in Rd, and intersecting that with an affine subspace. So this affine subspace, it's a translation of a linear subspace, which I'm going to call W. So this is all the elements of Rd that I can write as the kth entry is the inner product of x with vk. Another way to say this is the image of the matrix with rows given by vk. The fancy thing to say here is this is the linear subspace that our affine subspace is modeled on. It's the linear subspace that's given by the difference of elements in our affine subspace. All right. So yeah, where does this get me? Okay, this is kind of an interesting thing to do. Well, I think of Rd as actually being the Lie algebra of the dual, the dual of the Lie algebra of t to the d. So taking the dth power of S1. So as I mentioned before, so somehow the same ideas keep coming back here. Looking at an affine subspace in the dual of the Lie algebra has to do with taking symplectic reduction, taking a moment map level for the group, the subgroup perpendicular to that affine subspace. So we talked about the case of you have a hyperplane, there's an S1 perpendicular to that hyperplane in T dual, and restricting to that hyperplane has to do with reducing for that S1. So now I'm going to take my W, that's a subspace in the dual of the Lie algebra. So it has a perp subspace, which is d minus n dimensional, inside the Lie algebra of TD. And exponentiating, I get a subgroup, which I'll call G, inside TD. So the running example that I started with, I actually get the diagonal subgroup inside S1 times S1, right? So my subspace W is going to be when y1 is equal to minus y2. So the perp to that is the line going the other direction, so the diagonal. All right, and I've written it in this way, so it doesn't matter whether I use the exponential or the additive notation. So out of my polytope, I've now gotten a subgroup inside TD. And I want to look at T star of RD, or you could say CD. And it's kind of nicer to write everything in the complex way with the natural induced TD action. So this is what we wrote before of, remember, I'm thinking of TD as RD mod 2 pi z d. And so I have an action, which is just y1 up to yd here, maps to the diagonal matrix, whose entries are e to the I y1 up through e to the I yd. And that naturally acts on c to the d. And of course, that's going to be a Hamiltonian action since it's symplectic and linear. In fact, it has a moment map, exactly this one we saw before. This is a special case that it's just I take all of the different entries of my complex vector and I take minus 1/2 norm squared for each one of the entries. So this is just because the sort of action on each of the complex coordinates is boring. So the vectors I was calling U1 up through UD in the construction before are just the unit vectors in RD. And so I get this nice moment map, which is just taking minus 1/2 norm squared of the coordinates. All right. And so let me actually make myself a little bit of room here. I often find when I'm looking at this stuff, I'm like, oh, I didn't say things in quite the right order I wanted to. Note that the image of this is exactly this negative orthant. It's exactly the elements in RD. Forget now what I've been calling elements of RD, but it's okay. Say y such that all of the coordinates are less than or equal to 0. So you could sort of take, say, kind of, oh, the starting point for this whole connection between Delson polytopes and symplectic toric manifolds comes from really the fact that the action on C to the D by the unitary diagonal matrices corresponds to this negative orthant. And of course, you could complain both that that negative orthant isn't compact. Well, CD isn't compact either. So sort of both of these are non-compact manifolds, c'est la vie. Those sort of match up. And then, well, I'm going to write every polytope as the intersection of an affine subspace with this negative orthant. What's the corresponding operation on the symplectic geometry side? And the answer is it's reduction with respect to this subgroup G. So the dual of the Lie algebra of G, by definition, is RD mod W, right? The Lie algebra of G is by definition the perp to W. So its dual space is RD mod W. And the action of G is Hamiltonian with the moment map given by just taking this mu D I had before and taking the projection down to RD mod W. So we can think of lambda 1 up through lambda D, these numbers we fixed before, as a point in G dual, and we can consider the Hamiltonian reduction of CD at that point of G dual. So as we discussed before, you can sort of have a debate about whether I should have said subtract that from the moment map, but don't worry too much about that. All right. So I just want to note here how is this connected to the polytope? Well, this moment map level for the moment map of G, not the moment map of the whole torus, but the moment map for this subgroup, is exactly the elements of CD such that, when I take this -1/2 times the norm squared of each of the components, that lives in the polytope delta, thought of as a subset of RD. So for example, let's go to our running example. When I take this diagonal subgroup, so now I'm looking at the interval in R, I'd found that G was the diagonal subgroup. So when I take the moment map to that, I just sum the two coordinates. So I get -1/2 times norm Z1 squared plus norm Z2 squared. And the moment map level is a sphere. And it is true that if you look at this moment map for elements of C2, all of the spheres of different orbits, of different radii, are going to exactly map to the line segments here, right? Because I'm taking the norm squared of each coordinate, I'm going to have each sphere line. All right. So how do we think about this reduced space? Well, you have one answer here. You're thinking of the points in Cn, such that when I take a norm squared of the coordinates, they land in this polytope, and then I'm modding out by the action of G. But it's useful to think about the fact that because TD is abelian, right, that means that any element of TD sends a G orbit to a G orbit, because it commutes with all the elements of G. And so I get an induced action of the quotient group. This is something special about normal subgroups. And of course, every subgroup of an abelian group is normal. So I get an action of TD mod G, which you can check is isomorphic to Tn. Basically because we've chosen an isomorphism of, let me see if I can get this right. So, right, we're looking, if we think on the level of Lie algebras, what we're doing is we're taking RD mod W perp, well, that's W dual. And of course, we already chose an isomorphism from W to Rn. So I should have called this. No, I guess I'm calling it X. Okay. So I have reduced space X. It has an action of Tn, and this action is Hamiltonian via just looking at the moment map for the group Tn restricted to that level. So it's Hamiltonian with the moment map where I map to Rn, thought of as an affine subspace of Rd in the way we discussed before. Well, if you think about what's the image of the moment map, it's delta, right? So essentially by this observation, we found that we have a moment map and its image is delta. So theorem, this makes X into a symplectic toric manifold with essentially by construction, moment map image delta. Are there any questions? So I should emphasize again, I don't really claim that I proved this result. There's one obvious detail that we should check. I haven't used yet that my polytope was Delson, right? For any rational polytope, I could do this construction. So what's special about being Delson? So the only part of this that we actually really need to prove is why is it a manifold? Why is this reduced space a manifold? I.e., why does the group G act freely on that moment map level? Because if I know that it acts freely on that moment map level, then I'm basically just applying Marsden-Weinstein reduction. That'll give me the symplectic structure, and it'll be essentially automatic that the induced torus action is Hamiltonian. So where my Delson condition has to come in is it has to be somehow related to the freeness. And indeed, you'll find that the polytope is smooth. You can even say that the polytope is smooth at a given point. Smoothness is a condition about how the points coming in behave with each other, if and only if the action of G is free on the corresponding orbit. Okay, so let's talk about why this is. So what we want to look at is we have some point. How do I think about what its stabilizer in the subgroup G is? Well, the first thing to note is the only thing that matters is which coordinates. So I'm thinking of a point Z in Cn. So G is acting by scalar multiplication of the different coordinates by some scalars. And so it's going to act, what the stabilizer is only going to depend on which coordinates are 0, which coordinates are not 0. And indeed, the way to think about this is that G is the kernel of the map that takes an element of R mod 2 pi z to the d and sends that to using those yi's as linear combination, taking the corresponding linear combination of the vectors vi. And this guy is well defined precisely because the vi's are integral vectors. Right, so I'm using here, since vi is in z to the n. So if I take you have to be a little bit careful here, right? These yi's, they're not actually well defined as real numbers. They're only classes mod 2 pi z, but because it's okay to multiply one of those by an integer, it ends up being okay. And such an element stabilizes a point in C to the n if and only if the corresponding coordinate of the point is 0 whenever this yi is non-trivial. So these yi's, you should think of them as elements of the circle group. They're an R mod 2 pi z. And so if I'm going to be in the stabilizer, if I have a non-trivial rotation, the corresponding coordinate had better be 0. If I don't have a non-trivial rotation, then that's okay. The coordinate can be non-zero. All right. Now we can read off which of the coordinates are 0 and which are not by looking at the moment map image and looking at where it is in the polytope. So let me go way back up to the picture I had before. Right? When I look at this blue segment, the points where any coordinates are 0 are the ones sitting on hyperplanes. So the question of which hyperplanes bounding the polytope have non-trivial intersection is exactly the question of which coordinates can be 0 at the same time. Right? So in this example, we see O. We can't have the two coordinates be 0 at the same time because the corresponding facets of the polytope, this point and this point, don't have non-trivial intersection, right? So I avoid this point here where where both coordinates are 0. All right, so when I take the moment map image, right, I get a point in delta, and by definition, the inner product of that point with VI minus lambda I is equal to minus 1/2 norm squared of ZI. So this ZI is 0 if and only if the inner product of X with VI is lambda I, even if and only if you actually sit on the corresponding hyperplane. So for example, right, let's do a slightly more non-trivial example, right? I have 4 hyperplanes now. I'm going to have an element of Z4, right? And let's number our hyperplanes, 1, 2, 3, 4. So if I have a point here, this means that Z1 is equal to 0 and all the others are non-zero. If I have a point here, this means that Z1 and Z2 are 0, all others are not 0. And so on, right? So this is a point where Z3 is 0 and all the other ones are non-zero. This is a point where Z3 equals Z4 is equal to 0, but all the other ones are non-zero. And so just looking at the polytope, I can sort of see this pattern of which points can be 0 at a given time. So if for each point I can consider this set of indices where I lie on that hyperplane, I'll call that set S. So a point is going to be in the stabilizer. Well, for every coordinate that doesn't lie in S, the ZI is non-zero. So my circle coordinate has to be trivial because I have to not be rotating that guy. So I have to have that YI is in 2 pi Z if I is not in S. And on the other hand, the condition I need for these guys in S is that YI times VI, if I sum those up over the elements of S, that has to lie in 2 pi Z. So that's saying that on the coordinates that are non-zero, the YI is allowed to be non-zero because those coordinates are 0. And then this condition, this is the condition I need to be in G. All right. So just writing this a bit more carefully, we can identify the stabilizer of this point Z, I should say in G, with choosing yi's for every element of S. All the ones outside of S have to be trivial, or else I wouldn't be in the stabilizer, such that when I take the linear combination of Zi with these coefficients, Vi with these coefficients, I get something that's in 2 pi Z to the N. And then I mod out by the fact that these are only well-defined on the circle. So I'm modding out by 2 pi of Z to the S. So I'm just saying that, with the indexing set S. All right, so that's just kind of unpacking the definition. That's what the stabilizer is. And I'm interested in, when is this stabilizer 0 or not? So how do we understand this guy? Well, since my polytope is Delson, in particular, it's simple. And so I have an isomorphism from Rs to Rn. Oh, shoot, I'm lying a little bit here. Let me, for now, assume that my point is a vertex. Sort of the, yeah, I slipped a little bit here. So I should have said something more here. Okay. So let me adjust this. So what simplicity tells us is that we have an injection of Rs into Vi into R to the N. Which is given by taking the corresponding linear combination with respect to the VIs. And this is an isomorphism if and only if V is a vertex. So that's the simplicity condition. I want the VIs to be a basis of Rn as an R vector space. That's the simplicity condition, that I have my hyperplanes coming into the point, have normal vectors which are linearly independent, and they're a basis if and only if I'm at a vertex. If I'm not in a vertex, they span some smaller subspace, which is the perp to the face I'm on. All right, so I lied a little bit here. What I'm actually getting is that, so let me, if V is a vertex, then let's see what's happening there. So my elements of R to the S such that Yi, Vi, and I gotta take the sum here, is in the integral lattice 2 pi Z to the N. Well, that by definition gets mapped to 2 pi z to the n under this map. Like that, I've defined this set to be the pre-image of 2 pi of z under this map. And on the other hand, 2 pi z n maps to the span over z, the abelian group generated by 2 pi times vi. Again, just look at the definition of the map. So the stabilizer is the quotient of these guys. And what I should say is, if not a vertex, I have to intersect both with the R span of the VIs. Okay, so let's just focus on the vertex example for now. It's not going to matter much to look at other ones. So what this is telling us is the stabilizer in G of this point is gotten from, is Zn, mod the subgroup, the abelian subgroup generated by the VIs. So being simple means that this is finite, because the VIs are, have to span, they have to be an R basis, but they don't have to generate Z to the N as a subgroup. They just have to be cofinite. There has to be a finite quotient. And the Delson property is exactly that these two guys are equal. That this is equal to this. So the Delson property is like on the nose, the fact that these stabilizers are trivial. And somehow I'm sorry that I got a little messed up about the case of not being a vertex, but the point is somehow like being a vertex is kind of the most degenerate you can be. Having a stabilizer of a given size is a closed condition. So somehow if it doesn't happen at any vertices, it can't happen anywhere else, because every closed, because it's going to be the same everywhere in a face, and the closure of every face contains vertices. All right, so for example here, right, this exactly kind of comes down to the fact that I can't lie on 3 of these hyperplanes at a given time. Right? The simplicity condition is exactly telling me that at each of these vertices, I have exactly 2 hyperplanes coming in. And so when I look at the stabilizer, I exactly get, oh, those 2 normal vectors, they span Z2, there's no stabilizer. So this is sort of the other place the Delson condition comes in, right? So it's sort of worth thinking about how these 2 stories fit together. So we got the Delson condition before by saying, okay, I'm going to start with a manifold with a torus action and look at what happens when I operate on the tangent space, right? And here the Delson condition just tells me, oh, well, that's what I have to do to get a manifold. If I only have the simple condition and I don't have the Delson condition, so what's going to happen is then I will get finite stabilizers at points where the smoothness condition doesn't hold. So for example, if I take the x-axis and the y-axis and cut that off with the equation, px plus qy is equal to some constant. And again, a doesn't have to be an integer. A could be anything, but p and q should be integers. Then I'm going to get an orbifold. And the reason is exactly that when I look at these vertices, when I do my symplectic reduction, I'm going to have a stabilizer which is cyclic of order q, at this vertex and cyclic of order P at this index. And it's exactly that, you know, like something about the fact that when you look at complex numbers that are sent to 1 by being raised to the q, you get the qth roots of unity. So this is sort of where these stabilizers come from. So there are actually many more symplectic toric orbifolds than symplectic toric manifolds, right? It's kind of easy to write down simple polytopes because you can write down any set of hyperplanes and jiggle them so they're simple. But being Delson is a really special, powerful condition. All right. Are there any questions? So this is how we go back, how we start with a Delson polytope and get a symplectic toric manifold. And so if you recall, my list had 3 points. I've covered the point of why is the image a Delson polytope? I've covered why is every Delson polytope an image? Now I have to say something about, well, why is it unique? Why is, you know, why if I sort of, you know, add in a redundant inequality somewhere, well, I end up doing a different symplectic reduction, right? My D goes up. You know, I could look at a situation like this, and then, you know, I could add in another inequality that corresponds to this hyperplane, right? And now instead of reducing R3, I'll be reducing R4. And by, instead of having a one-dimensional torus, I'll have a two-dimensional torus. So why do I get the same thing? And as with all of these, I'm not going to try to give you a like extremely detailed proof, but sort of there's a nice cartoon of a proof, which I think gives you at least a little bit of insight. So if I look at the interior of delta, then the Tn orbit over all of these points is free. If I have a point where the action, an orbit where the action isn't free, you can show that I'm on a wall of my polytope. I'm in a non-trivial face. So actually what happens over the interior of the polytope is my moment maps down and I get a trivial T principal bundle. And I can trivialize this symplectically by thinking of T star times the torus as the Lie algebra, as the cotangent bundle of the torus. That has a canonical symplectic form. I can translate that over to delta 0 times Tn. And I can choose a symplectomorphism to my M0, which is T equivariant. And definitely one of the points I'm cheating here is how do you make a really good choice of this? Somehow you might think, okay, when I've chosen one, like what choices of other ones do I allow? You know, and I don't want to allow myself to do something crazy, like start wrapping around the torus really fast, right? If I have 2 of these, they're going to differ by on each fiber acting by an element of the torus. And I don't want to like start doing one really fast where I sort of don't end up with a good limit as I go to the boundary. So I'm being a little vague here, but if I choose this in a good way so it doesn't kind of blow up on the boundary of the polytope, then I'm going to get an induced map from the closure of the polytope times the torus to my symplectic toric manifold, just extending by continuity. Now, that is not going to be a bijection. And the reason is, if I'm on one of the faces, I definitely will not get a free orbit above me, right? As we discussed before, if you're sort of on a face, then in directions that are transverse to the face, you can't be getting non-zero derivatives. The tangent space, the face you're on, is actually the image of the derivative of the moment map. So let me just take this. Oops. If X is in the interior of some face F, then the image of the derivative of the moment map is equal to the tangent space to this face. So the stabilizer of this guy is going to be non-trivial. Oh, I don't think I gave this a name. So the stabilizer of a pre-image, well, that's the kernel of the derivative, is going to be equal to the perp to the face, exponentiated. Which I'm going to denote TF. So for example, for a vertex, it's a face that's zero-dimensional. So the whole torus acts on a stabilizer as the stabilizer of the preimage. The preimage of a vertex is going to be a fixed point. On the other hand, if I take some point in the interior, the face it lies on is all of delta. And so the stabilizer is going to be trivial. So subtorus TF corresponding to my face. And so the existence of a non-trivial stabilizer tells me that this map is definitely not a bijection because the source has a free T action and the target doesn't. All right. But that's actually the only thing I need to account for to make this a bijection. So on this domain, I can add an equivalence relation, which says that if my point down in delta is on a particular face, and differ by an element of the torus that's supposed to be the stabilizer, then I identify them. So I'm essentially forcing by hand points to have the right stabilizer. Just say, okay, well, on each fiber, I mod out by the action of the group that's supposed to be the stabilizer. So this means that this map down to here is now a bijection. And well, there's some version of this uniqueness proof where you look at this orbit space and you say, okay, here's how I'm going to make this orbit space into a manifold. And oh, look, it's a symplectic toric manifold. So things are unique. That's actually like it's a little bit annoying. It's not like that hard, but if you sort of think about what's happening as you come up to a vertex, right? That moment map involves a square. So you have to be like careful about what happens at when you come up to a vertex. Like, you know, think about if you had C and you kind of only had like set theoretically or topology without the manifold structure, the map down to R of norm squared, how would you like, you know, it's, yeah, so let's talk about this in that case. So assuming, you know, so I start with C and I have norm squared, so this maps me down to R plus by, for each point here, I have my circle, which is a pre-image. And what the construction I did before does is it says, okay, well, I can take R plus multiply that by a circle to get a cylinder, right? And the map of this down to R, indeed, this becomes a bijection with C if I take this circle here and smush it down, right? So what this construction says in this particular case is there's one edge, one vertex here, this guy, and on the fiber over that guy, I smush everything down to a circle. And so indeed, if you take a cylinder and you pinch that circle down to 0, it'll look the same as a plane topologically, but like think about what's happening with the manifold structure there, right? It's not the manifold structure on the plane that's just induced by the manifold structure in R. You have to stick in like a square root somewhere. So I think there is a way to do this where you just think very carefully about that and write down the right sort of formulas. I think there's an easier way to do this, which is to say, okay, I found a bijection, and I just started with any old symplectic toric manifold that has the right polytope. So if I had another one, I could construct a bijection from this quotient space down to that guy as well. And so now my two symplectic toric manifolds, which already had manifold structures, are in bijection with each other. I have a map from one to the other. And of course, then there's a bit of work to check why is that map a diffeomorphism. I claim it is. I claim that this becomes sort of a local issue. You only need to check it sort of, around each point, being a diffeomorphism is local, and somehow it really only reduces to the case of a vertex. Somehow if you have some point that's on a face that isn't a vertex, like you can sort of think of it as something boring and smooth going along the face and something that looks like a vertex for a smaller polytope going the other way. And then you can do it by hand. Then you just sort of look at, okay, well, what happens locally around a vertex? I have my equivariant Darboux coordinates on the two sides, and this map just matches them up. And again, that basically just means look at this case and think hard about what's going on. Right? If I had some other guy mapping down here via the moment map to R plus, I would be able to put it in bijection with the cylinder. And whatever this kind of slightly funny behavior around the circle that's getting crushed out is, the other guy would have to have the same slightly funny behavior involving like square roots. All right, I'm out of time. So as promised, we said everything I wanted to say about symplectic toric manifolds. Are there any questions?
I have some sort of questions, but they're kind of specific to the fact that I have some specific interest that this has hit upon in a way that I wasn't quite expecting. So I should probably let other people ask questions if they have more like general interest, questions about just the talk, the lecture as such.
Yeah, I wouldn't expect too many of those.
Well, okay.
Do you want me to keep recording or not?
I guess no. I mean, I don't care. I mean,